Okay, so in these problems, let's have a look. We want to prove that 1 cubed plus 2 cubed, 3 cubed, through to the general term of n cubed would be equal to 1/4 n squared outside of n plus 1 all squared. Again, we start with showing it's true for n is equal to 1, so we substitute 1 in. 1 cubed on the left-hand side would be 1/4 times 1 squared times 1 plus 1 all squared. And we calculate that. Throw in your calculator or do your own calculations. It comes out to be 1, nicely. Step 2 is assuming it's true for n is equal to k. So n is replaced by k in that statement. And we're assuming this is true. We're assuming the sum of all the cubes is equal to that statement. So then we go to step 3. Now, keep in mind what we're requiring to prove. When n is equal to k plus 1, we would get 1/4 of k plus 1 all squared, k plus 2 all squared. Remember what we're trying to prove. K plus 1's being thrown in there. So k plus 1 all squared, k plus 1 plus 1, which is the k plus 2 all squared. If we get to that, then we've proved it. So we start with our left-hand side. We've got the sum of the first k plus 1 terms, and we need to get down to this statement. So again, our problem is our unknown terms there, but from step 2, we know we said that the sum of the first k terms of this statement would be equal to this statement here. So we do our substitution. Now we've got no missing terms, and we need to get down to what we need. Let's factorize. What can we factorize out? K plus 1 all squared. Well, k plus 1 all squared can come out of that. So there we get our k plus 1 all squared factorized out. We want a quarter out. We've got a quarter in our first term. Factorize it out. We've got 1 there, so we can factorize a quarter out of the 1. Gives us 4. Nothing we can factorize here to get us down, but we do want k plus 2 all squared. Can we expand that one out and get down to what we want? K squared plus 4k plus 4 comes down to a perfect square of k plus 2 all squared. Nicely, that is true, and we can make our statement in step 4, which we haven't got there, but you can make the statement in step 4 as we've made before. In this next problem, we've got the sum of the consecutive odd integers. 2m minus 1 there is our general term. It'd be equal to n squared. So again, prove it's true as n is equal to 1. 2 times 1 minus 1 is 1. 1 squared is 1. It's true. Again, we make our assumption that n is equal to k. The sum of the first odd integers is equal to k squared. What we should be looking to prove is that the sum of the first k plus 1 integers, odd integers, equals to k plus 1 all squared. So we start with our left-hand side to prove that our right-hand side is true. Problem with our terms there, but there's our sum of our first k odd integers, and we're left with this statement, 2k plus 1 and minus 1. So we know that was equal to k squared, which will do a substitution. That comes down to the k squared there, so we can put that in. This leaves us with 2k plus 2 minus the 1. Clean it up, we get k squared plus 2k plus 1, which can be factorized to k plus 1 all squared. Therefore it's true. Step 4, we can say that. So we can see how we're manipulating our algebra every time to get down to what we want, and it should get down there, otherwise we haven't proved it. This time the sum of the squares of the odd integers, the 2m minus 1 all squared, would be equal to this statement, 1/3 of n, 2m plus 1, minus 1, 2m plus 1. So show it's true for n is equal to 1. So sub the 1 in, gives us 1 on this side, 2 lots of 1 minus 1. Yep, so that's 1, which is 1 squared there. So we substitute it in, do our calculations. We get a half cancelling with the 2, the 1 one's there, the 2 one's there. Sorry, the 1/3. That should be a third in there. Cancels with the 3 there. That's a little bit better. And so we were able to get it's equal to 1. Assuming it's true for n is equal to k, so we start do our substitution, and we're going to be able to make a substitution of that part and put that one in step 3, hopefully. So what we need is a substitution of k plus 1 in this side. Sorry about that. So what we're looking at is requiring to prove in the next part. That's where we do our k plus 1 and putting that part in there. And we should get a statement that looks a bit like that. So you see how our decomposed would look like that. So we want to put it back. As long as we can get it into those, we've got it proved. So again, we start with what we had in k plus 1. We substitute. There's our sum for the first k terms and our k plus 1th term. And then what we need to do is do our substitution, because we, again, got unknown terms. Put our assumption in from step 2. So we know that was true, but we can make that statement there. The 2k plus 1 minus 1, so we can expand it out. We get 2k plus 1, and that's all squared. Now, keep in mind what we want to prove. So we want to get a 2k plus 1 out, so factorise that out. It's common to both. You got 2k plus 1 out. We factorise our third out in the first term, so it's a 1 there, so we factorise the third out of the 1 gives us 3. We're left with 2k plus 1 in our second term, the k, 2k plus 1 there. Can't do much else. Let's expand it. We get a quadratic, so it's not too bad. If we get a cubic, that's what we said, it's going to be a problem. But it's only a quadratic here, so expand our terms out, collect our terms. We get 2k squared plus 5k plus 1. We've got a third, and we've got the 2k plus 1. Hopefully this comes down to k plus 1 and 2k plus 3, which when we look at it and do our factorization, it does. It's true. So it works for n is equal to k plus 1, because that's what we get. We get to the statement if we substituted k plus 1 in, and we've actually proved it. So we haven't got step 4 again there, but we can write in step 4 as we normally do. That's true for n is equal to 1. It must be true for 2. And it must be true for 3, and so on.